This is an example of a projectile motion problem. Let's read the problem statement. A pitcher throws a baseball horizontally with a speed of 90 miles per hour from a height of 6 feet. If the batter is 60 feet away, determine the time needed for the ball to arrive at the batter and the height h at which it passes the batter. Whenever I start a projectile motion problem, I always look at the figure and label key points and add key information. This helps me visualize what's going on. So let's do that. All right, so you see here that I have added a few things to the figure. The first thing that we need to add is a coordinate system. So here I have the X and Y coordinate system, and it shows where I've located my origin. So the pitcher is going to be where the X direction starts as 0, and the ground is going to be where the Y direction starts at 0. All right, the next thing I did was label the two key points. So you can see here the pitcher, I labeled A, and when the ball arrives to the batter, I've labeled that B. I've also put the velocity on, the initial velocity. They said in the problem statement that the pitcher throws the ball initially with 90 miles per hour horizontally. So that means that there's only an X direction, no Y direction at the start. Of course, the ball will accumulate Y velocity as it goes to the batter, but initially there is none. You can also see I've labeled the height that the ball is initially thrown as being YA, because that is the height of the ball at point A. And also a big H, which we want to find, I've labeled that YB, because that's the height of the ball when it reaches the batter. And then we have the distance between the pitcher and the batter, which is 60 feet, and I've labeled that XB. All right, so the reason why the coordinate system is so important in projectile problems is because we usually break up this type of motion into the X and Y direction because they're independent. So we essentially make this two rectilinear problems. So it's very important to include the coordinate axis in your figure. I usually start my analysis with the X direction because it's usually the simpler direction. One thing that makes it simple is that the velocity in the X direction is constant, assuming we neglect air resistance. So the velocity equals dx dt. If you integrate that, you get x equals x naught plus vx naught t. So we can apply that equation at point B, and that will give us the time it takes the ball to get to the batter. So if we apply that equation to point B, we have xb equals xa, which is our x naught, plus vx naught tb. So we know what xb is, that's 60 feet. We know what the velocity at the pitcher is, but we have to make sure we change that from miles per hour to feet per second, and we can solve for time. Now we can go to the y direction. Now what makes the y direction special is that the acceleration is constant and equal to minus g. We know that acceleration equals dv dt. If we integrate that, we get this next equation for the velocity in the y direction, and we know velocity is equal to dy dt. We can integrate that and get the position of the ball in the y direction. However, the equation sheet does that for you and automatically gives you the position for the ball in the y direction. So you don't have to integrate, but it's nice to know where that equation comes from. So we're going to apply this equation at point B, and we get YB, which is capital H, equals YA, which is the initial, plus VY naught, which is 0, minus GTB squared over 2. So we know everything in this equation except for H, so we can solve for H.